Our next presenter is Cory Harris. He is the Watershed Services Coordinator at the Ganaraska Region Conservation Authority and one of the two engineers that Jeff is sandwiched between. And I know Jeff told me engineers love their contours and they love them if they're sub-centimeter. So part of this is the physics and the accuracy, chemistry of water, which is what both Cory and Christopher are all about. But prior to that, uh, Cory was the water resources engineer at Halton Conservation Authority, and he survived the Burlington deluge of 2014 when 2 months of rain fell in one day, flooding 500 basements and costing insurance companies over $90 million. So with that, Cory, tell us how you're using the open data, the new tools to try and adapt to extreme weather events so that we can prevent the damage from flooding.
Thanks, Jonathan. Yeah, the Burlington flood was a significant event, and it was I think, a learning experience for a lot of folks. Excuse me. One of the things that became apparent out of that is just as practitioners, we need to start using more innovative tools and defining how flooding will occur in floodplain areas, but also floodplain areas that are in close proximity to urban areas. I'm just going to share my screen here. Okay. Okay, can everyone see that?
You're good.
Okay, excellent. Thanks. So what I wanted to touch on today is using one of these innovative tools in helping to better define flood susceptible areas, particularly within urban areas. And my area of focus is on two-dimensional models. Historically, conservation authorities, as well as engineering consultants, we've relied heavily upon one-dimensional hydraulic models to really define the floodplain limits for a given creek or water course. That has served us really well, and it really shines when you've got a defined valley with, valley walls and a top of bank, and the flood waters are essentially contained within the feature. Where it breaks down is where the definition of that valley is not significant, and it's kind of lost within urban areas and is considered an unconfined system. One-dimensional hydraulic models really rely on cross sections across the valley and watercourse feature. So it's picking up the topography and it's calculating water surface profiles based on these cross sections and the gradient of the overall watercourse. What happens in an urban area when water starts leaving the creek and starting to move through the neighborhood, these older one-dimensional models assume that all the flow is going in a downstream direction. So one-dimensional directional flow. We know that in an urban area, especially when you've got buildings and other obstructions, water actually fans out and behaves in a different manner. And you have to really assess where the water is going in 2 dimensions. That assumption of one-dimensional flow no longer really works. So these 2-dimensional models rely on the physics of wave diffusion to represent these flow patterns. And one of the things we really like about 2-dimensional models is it provides outputs that are fairly intuitive for folks to understand. And as Christopher mentioned, engineers aren't that great at communication at the best of times. So when we find tools that help us explain the work that we've done and what it means, that's a real plus. So one of the things that we've really relied upon is LiDAR data. LiDAR stands for light detection and ranging, and really what it is, it's a remote sensing product that's acquired through by a plane flying over an area and measuring the ground surface with millions of basically laser points that bounce up off the ground, and the equipment in the plane can measure with a high level of accuracy what the ground elevation is. And when you put all those millions of points together in a point cloud, you can then build a digital terrain model, or DTM. When we look at the inputs to a two-dimensional model, this is where the LiDAR really and the DTM really shines. We're able, instead of just doing a cross section every so often along the water course to represent the hydraulics, we can create a mesh over top of the DTM surface, and you can then assess how the water will move from each cell within the mesh. So as it's elevation's rising in one cell, it kind of checks with the surrounding cells, and it knows, okay, the ground surface is lower in this cell, so the water is going to go in this direction. So the work that Jeff and others do is absolutely essential to providing data for these types of models. So the example that I want to show briefly today is just Midtown Creek at the bottom end near the harbor in downtown Cobourg. So here's a picture of that area. You can see Town Hall. The beautiful Town Hall is just to the left of center here. So when you look at that same area with a digital terrain model and a buildings layer, this is what it looks like. So now that we've got those data sources, we can then build our mesh over top of that DTM surface and add in other things like the section, that red line is representing where the creek has been buried historically. So we've represented that in the model. We've identified all the buildings so that the mesh develops around the buildings. This is just a closer view of that area, and it's north of the main street. So at the top end of the image, you can see the open channel where it goes into a buried pipe system in red here. And what I wanted to do here is actually just share my screen and show you some of the features actually out of the model itself. So I've got the air photo turned on. If I turn that off, you can see the DTM below. But just for reference, I'll leave the air photo on so you can see and just have reference points here to understand what's happening. So one of the other inputs into the model is a hydrograph, a flow hydrograph at the top end of the study area. So we would run the whole hydrograph from an event, and this one that we're showing here is the Hurricane Hazel or regional storm event that conservation authorities are obligated to regulate to. And so I'm going to play an animation so you can see just how the regional storm would progress through this part of Cobourg. And each time step is approximately, I think it's 15 minutes. So you'll just see how the water starts backing up behind the channel and spilling out from the banks. And then it's just slowly flooding some of the buildings at the top end. It's then going to progress into the parking lot just south of this area. And you can just see how when the hydrograph flows increase, you really get a sense of how much of an area is flooded. So it's just a very helpful tool to use when you're assessing flooding impacts. And if I zoom in and I back it up here to one of the peak times, you can actually look at particle tracking, and it shows flow directions and kind of the hydrodynamics of an area to show where the water is going and what the flow patterns are and how they move around the buildings. And you can also look at velocity vectors. So if you want to assess risk levels, the bigger the arrow, the faster the velocity. And you can really get a sense of, in a flood event, where are the greatest areas of depth and velocity, which are the problem areas. So yeah, I think I might be a little bit ahead. I'm not sure, but I'll end it there. I'm happy to answer any questions.
Well, we'll hold the questions, but I will ask one thing. That's fantastic. I know that Ian, who does the AI stuff with Jeff, he did a presentation at Go Open Data 2 years ago, and he used the same example, but he also talked about emergency response. So with the velocity, can you sort of how would that be used to support like an emergency response during an extreme weather event?
Well, with this information, we can look at how a structure like a bridge or culvert structure is performing in different flood events. So if water actually backs up and overtops the road, we can look at what are those depths and velocities, and is it safe to actually rely on that route in an emergency? So there's criteria from the Ministry of Natural Resources and Forestry, and so we can identify those zones that are essentially unsafe in a flood event. And we also use this in reviewing development applications for folks that are already in the floodplain and confirming their ability to safely access and leave their property during flood events. So it's a tremendously helpful tool for those purposes.